happy faces this morning. I got some feedback just from questions and discussions yesterday. So let me recall some things that happened last time and fill in some things that seemed useful to say yesterday. So I tried to highlight the new parts in pink. So last time, I motivated with that cartoon kind of what the theme is for this. And then I stated this main result that we're aiming for. Of course, I haven't explained any of these terms, but that's where we're going. That there's a fully faithful functor of infinity categories from pointed infinity n categories to space-valued functors on a certain category of stratified n manifolds equipped with a strong notion of framing. And that functor is factorization homology. And that's compatible with a likewise functor with this traditional notion of framing on manifolds, just framing of the ambient manifold, regardless of the stratification. And in that case, it respects infinity n categories pointed that have adjoints. So that was the end of like the motivation part. And then I sketched the definition of stratified spaces. And I think there was, so something I want to clarify is that the objects of that category are far less important than the morphisms or the automorphisms in that category. All that regularity, it was not to have the right objects as much as to have some control on the automorphisms of those objects.
So where do stratified spaces fit into your diagram?
They don't. They index everything two layers back. They're in the room. This is in the left hand. That's right. Yeah, and the right-hand side. Everything.
Wait, the right-hand side, I understand. Manifolds.
It's a category that you probably are not aware of.
It's not.
Well, it's a category of manifolds, but we'll get there today maybe. So I just wanted to include this here because if you just don't care about the regularity, you just want some idea of what I mean by a stratified space, this will suffice. So we have this with Hero in our paper. A C0 stratified space, so no smoothness around, is the smallest collection of paracompact Hausdorff spaces equipped with a map to a poset having these properties. The first is that the empty thing is an example with the empty poset as the target. The second is that if you're given a compact one, such as the empty set, and you take its open cone, resulting in a point, that's an example. Also, if you're given something that's an example, you can cross it with R. So just already we have Euclidean spaces, are examples. A next property is that if something's a stratified space and another thing openly embeds into it, then the domain of that open embedding is also in there. So it's closed under subsets. So now we have that all open subsets of Euclidean spaces are examples. And then the last property is if you're given an open cover of something in there, where every term in the open cover is in there, then the thing it's covering is in there. And that generates a gigantic class of spaces, but it's the smallest one. Any candidate for what you mean by a stratified space will certainly satisfy these. So this is like the smallest collection you could maybe imagine. And that's it without any regularity.
And morphisms would be just arbitrary?
Yeah, because really the regularity is to say what morphisms I want to allow. I'll say yes to that, but I don't care so much about what the answer to that is for the unregular case. Okay, so then there was an ordinary category of stratified spaces and conically smooth maps among them. Inside of that category was smooth manifolds. And then there was the Kahn-enriched version, curly strat. which we'll immediately regard as an infinity category, though it's useful to know it came from a Kahn-Rich category. And the following things are true about curly strat. I didn't mention this last time. So the first is if you're given an open cover of a stratified space, then you get a cone-shaped diagram, and therefore you get a cone-shaped diagram in curly strat, and the assertion is that that's actually a colimit diagram in curly strat. So that uses partitions of unity to verify that. The second is that projection off of a Euclidean space is an equivalence in curly strat. That makes use of this Kahn enrichment. The third is that given one of these blow-up diagrams, so this is a closed union of strata in X, and we take the sort of real blow-up of that and produce this square. This is the link of that, and that's like a stratified space with corners for which that's the corner data, or the boundary, or whatever. So this is a square among stratified spaces, and the assertion is that that's a colimit diagram. So that's a push-out square. Yes?
So, for instance, when x0 equals x,
Uh-huh.
what are the spaces that you're imagining for this colimit diagram?
Yeah, so in that case, everything is, so this is empty. That's, I wanted to say is empty.
But then you don't have a
Something like that. Well, empty mapping to X is still constructible. Yeah. Yeah. So 4 is, there's this square. So here, by the bar, I mean the closed cone, maybe the more familiar cone. So given a compact stratified space L, we can take its closed cone. And the empty set embedding into it induces a map of cones like this. And also, the cone mapping in as the boundary of the double cone gives you a map, a vertical map like this. So you get this diagram. And what's interesting is that this diagram is a colimit diagram in curly strat. So this, unlike the first, unlike part 3 and part 1, this is not a colimit diagram in the regular ordinary category. This is only a colimit diagram in this infinity category. This will be tantamount to the Siegel condition ultimately. And then the final thing is that this is a colimit diagram. So here I have the 3 simplex standardly stratified, and including into it are these 2 1 simplices, including.
Let me just check I understand this correctly. So one is the cone, one is the unreduced suspension, 1 cone point and 2 cone points, and then.
Yeah, this is the double cone. So I take the cone of the cone.
Oh, the cone of the cone.
Yeah. Yeah. Yep. So if you, this diagram also is a colimit diagram in curly strat. This is tantamount to the completeness condition. So that's it for the pink facts for now. So last time we talked about this fact, that the map from the localization of the ordinary category, localized on projections off of Euclidean spaces, is an equivalence of infinity categories. So that gives an explicit way of you could interpret this as having an explicit description of the mapping spaces of this localization, which you might not expect are so easy otherwise. The next fact, this one, is that this cosimplicial object given by the standard stratifications of simplices is fully faithful. So again, that's not true in the ordinary category strat, but it is true in this curly strat. From that, we get this restricted Yoneda functor. strat to presheaves on strat. You can just probe every stratified space by these standardly stratified simplices. I'll call that functor star. The next fact is that star is a fully faithful functor, or factors, and it does so as a fully faithful functor, strat to infinity categories, here regarded as complete Siegel spaces. And this functor exit, called exit path category, and it's given by this expression. It sends a stratified space K, X, to, well, the simplicial space, whose value on a bracket P is this Kahn complex. It's stratified maps, or conically smooth maps, over these extended simplices in that way. So that's like the singular complex of X, but in a way that accounts for the stratification. And what I didn't mention last time, because I didn't mention the previous pink, is that this functor exit, it respects all of these 5 properties. In other words, it sends 1, 3, 4, and 5. Those are colimit diagrams. It sends those to colimit diagrams. So it preserves those colimits. And for part 1, obviously, it sends that map to an equivalence. So with this fully faithful functor, you can play the same trick again, and you get a functor, a restricted Yoneda functor from infinity categories to presheaves on strat. I'll call that functor double star. And the last fact, a theorem, is that this functor, too, factors as a fully faithful functor from infinity categories into presheaves on strat. And we identify the essential image of this, striation sheaves, we call them in this paper. And that's those presheaves that respect 1 through 5. So it's those presheaves that send 1, 3, 4, and 5 up to limit diagrams. In particular, part 1 says that it lands in sheaves. Part 2 says that it lands in what's called constructible sheaves. Part 3, you can interpret as saying it's those constructible sheaves that are satisfied descent with respect to a stratified version of the H topology of algebraic geometry. 4 and 5 are the Siegel and completeness conditions, essentially, which is maybe is what relates these things to these. So for my purposes, the reason for these developments is to produce examples of infinity categories. So and that's what I'll start with now, is showing how this can give you easy ways of describing infinity categories that I don't know how to describe in any other way. Okay, any questions?
So, is there a description of the essential image from code strat that pushes on top?
Of the essential of this? No. Someone asked that earlier. I would be curious. It's fully faithful, but I don't know. I have I know some conditions that the image satisfies, but I can't characterize it. Excuse me, I'm going to use the water. Sure.
Could you elaborate on how 4 is the Siegel condition? I don't quite see that.
How what?
How 4 corresponds to the Siegel condition.
Oh, sure. Thank you. I'll erase the board on that. so take L to be simplices. And so that's because of the fact that the closed cone on the p minus 1 simplex is the p simplex. So that's the way of, so what's on the top left is just a point. What's on the bottom left is delta 1. What's on the top right is, if I take L to be a simplex, is another simplex. And what's on the bottom right is a simplex of 1 degree higher. I hope that answers your question. OK, so I said that this will produce examples. So let me give 2 examples.
This is much more general. I mean, this is now showing that one implies the other.
Yes, that's part of, yeah, that's right.
So you're saying the seed condition implies this for all concepts.
Once you have the locality for the first three points. Yeah, and you can see I don't know how to write the completeness condition in a way that doesn't really depend on simplices. So here's an example. Let's fix a smooth, and let's just say compact for simplicity, manifold. M. So there's Ron of M. So you might know this as a topological space. Let me tell it to you as one of these, because this will be a unitary version of that one. And I'll make an assertion in a moment that if you know what that stuff is, you might find it an interesting assertion. So I'm going to describe an infinity category. So to do that, I'll tell you what this is as a pre-sheaf on stratified spaces. And I'll just comment maybe on why it satisfies 1 through 5. But what's the data of this thing? So that's an assignment of every stratified space K, some space. And it's this space, the space of the following stuff. It's an E mapping to K as a proper constructible bundle with discrete fibers. Oh, sorry. Let me write that a little bigger, I guess. And I'll just say finite fibers. So proper or constructible bundle with finite fibers. So that's the first part of the data in this space. And it's not quite over K, but K cross the extended simplices just to make this thing into a space instead of a set. Oh my goodness, this. Here's an identity map. And then the other part of the data is an injection from that into M cross K cross delta bullet E, mapping down that by the projection. That's it. So I'm describing a space for you, and that's the value on a stratified space K. So let me explicate this. What? That it does so injectively. Yeah. Yes, but it's the convenient way to, so it's like fiberwise injective map from E to M.
Oh.
Yeah. So let me just make the claim. So this is the data, and then you know what to check. It's the 1 through 5. This is, I just call it striation sheave. Which is to say it's an infinity category. So what's the space of objects in the space of morphisms? An object is, take K to be a point, and take bullet to be 0. So in that case, we just see a finite set mapping to point, and an injection of that finite set into M. So I'll just say a finite subset of M. So that's an object. It's a finite subset of M. What's a morphism? A morphism is a constructible bundle over delta 1. Take bullet to be 0 again. So let me just give an example, or just draw an example. So that's delta 1. And I'm going to name a constructible bundle over delta 1. Its fiber over the left dot is 3 points. The fiber over everything else, I'll say, is also 3 points. And it's all connected together like that. You see that's, I just drew some shape. It's a stratified space. It maps, it projects to delta 1 in a pictorially evident way. And it does so as a constructible bundle, because over each stratum individually, it's a fiber bundle. So a morphism is that data, together with an embedding into M cross delta 1, an embedding over delta 1. So I read that as a movie of finite sets that starts at this 3-element finite subset of M. And in the first moments, one of the elements is just deleted. And you see another element split into 2. And then these now 3 elements swim around for a while in the manifold without interacting, and then they stop. So this is non-invertible because this is not a trivial bundle. So fact, this pre-sheaf on stratified spaces is not representable. And it's not for kind of 2 reasons. One is that if it were representable by some stratified space, that would have to be locally compact, and there's just no way that this could be so. But another obstruction for representability is that stratified spaces have the property that their exit path categories are such that every endomorphism in them is an automorphism. And because of this ability for points to just be forgotten, then you can have endomorphisms that are not automorphisms. So this is far from being a stratified space. And if you know what the Ron space is, you might appreciate that point more. Let me give the main example.
What does Ron stand for? Is it abbreviation of something?
The guy, last name Ran, or Ron. Someone else can comment if they know more.
So, if you restrict your species to the delta p,
Yes.
you get that.
That's your infinity category.
That's this little S1.
Yep. So here's another example, and this is the main example. Bun. So this is an infinity category that I'll present as a pre-sheaf on stratified spaces. And as so, it classifies constructible bundles. This is the pre-sheaf that classifies constructible bundles. kind of like the disjoint union of B diffs of all manifolds classifies fiber bundles. And fiber bundles being locally trivial has something to do with disjoint unit of B diff of all manifolds being a space, a groupoid. So this is given by sending a stratified space to something I hope is a little bit motivated. This is just constructible bundles over K, and I put in the delta to make it a space. That's it. I wish I could express how long it took to come up with this example. And it's so easy to write down. So a fact that I'll write as a theorem is that this is lies in the essential image of that functor. So this is an infinity category. And proving this, so this is the hardest thing I've said so far to prove. Really, all of these developments were surrounding just proving that this thing is an infinity category. And this is just a natural way of presenting that. Hardest so far. So this makes heavy use of the resolution of singularities. Oh, definitely. Thanks. That's important. Recall. A conically smooth map. X to K is constructible so it's a condition if for each stratum the restriction is a fiber bundle.
Are there any conditions on the fibers or the structural?
Nope.
On the morphisms of any space?
Oh, well, it's in the category of, yeah.
But if I look at the structure, it is conically smooth homomorphisms?
Yes. And what's convenient about the smooth category is that, it's a condition for a map to be a bundle, a smooth bundle. And that's likewise here. Yes, exactly. They're the ones that are defined using analysis a little bit. Limits, difference quotients. That's what I refer to, yeah. Sorry, thank you. Oh. Okay. Let me describe an object and a morphism of Bunn. An object well, let's see. An object of Bunn is a constructible bundle, or so take K to be a point, And to describe just an object, not trying to say what the space of objects is, take bullet to be 0. So in that case, an object of bun is just a constructible bundle over a point. That's just the stratified space. That's an object. So like a smooth manifold, that's an object. A morphism let's see. Let's take k to be delta 1, and again bullet to be 0. So in that case, we say a morphism is a constructible bundle over delta 1. Let me draw a picture of that. So it's a constructible bundle. X to delta 1, which is that stratified space. I separated it out a little. Here's a picture of one, and I hope that this captures. I think this picture demonstrates everything. So here's delta 1. And over it, we have this. So the open things are to mean that the point's not there, as usual. When I drew this in my notes, I realized I should use color. So okay, what I drew so far is an open interval with 2 dots on it. That's a stratified space. That's what lies over point. Over here, we have so the pink is there. It's just behind, it's out of view, unlike that white. So the fiber over the other point of delta 1 is a circle with 3 dots on it. That's another stratified space. So what I'm describing is going to be a morphism from an interval with 2 dots to a circle with 3 dots.
The dots are things that have some lower stratum of that.
Yes. And it can go like this. So that dot can just be forgotten immediately. This one go like that, and then a dot can happen where there was. That's an example. So you can see that.
Second circle above the bottom circle.
Yeah. Let me exaggerate the cylinder just a little to make that more clear. They're strata. Does that answer the question? So the 2 kinds of dots. You mean the open dots and the closed? The open dots are just not there. It's just my way of, I could have drawn this, and then you'd ask, does that end or not? This thing, is that an open or closed interval? And that's just my way of saying it's an open interval. So there's no, it's not part of a stratification or anything. Alternatively, I might just erase them. Okay. So there you go. That's an example. Let me throw on one more thing to illustrate a little more with this example. We could have also taken a disjoint union of this interval with 2 dots on it with an interval with 1 dot on it. That's another object. So that's another fine object. And I just modified this, so now the source of this morphism is an interval with 2 dots on it, disjoint union a circle with 1 dot on it. The target of this morphism is a circle with 3 dots on it, disjoint union a point, and that's a morphism. So this illustrates a few kinds of phenomena simultaneously. So the first, I'll say these in words, then I'll write them down. The first is, this demonstrates a class of morphisms. Namely, this is really just the data of a choice of a stratum. This is just a choice of a closed stratum in that circle. Once you choose that closed stratum, then you can define one of these. So it's like the opposite of closed embeddings, inclusions of closed unions of strata. That's an example of a morphism. Here, if I just erase all the dots stuff, that would give me another example of a morphism. And that would demonstrate an open embedding from an open interval into a circle. And I call it that because, to actually get the open embedding, I'll have to make some choices. Those choices are contractible, such as a horizontal vector field. Once I make that choice, I can flow this interval until it hits the other end, and then I see my open embedding. So this is like an unstraight version of open embeddings that's very convenient. So open embeddings give other examples of morphisms. You also see here that a dot can just be removed. So refinements are examples of morphisms. And the last class, again, I'll write all these down, is you can see dots separate into more dots. You can see strata anti-collide. That's another class of morphisms. And so I'll write those down here.
You have also write the dot appearing. That's another one.
What?
The third one is also a dot appearing.
Yeah, that's like an open embedding, but of stratified stuff. So there, I could have said it's an interval embedding into a circle that had a dot in it, and the interval just missed the dot. So lemma, there are monomorphisms of infinity categories. So there's 4. The first is curly strat proper constructible embeddings, or injective, I'll say. So injective proper constructible maps op into bun. So that captures this phenomena at the very bottom. There's another class of morphisms, which is curly strat proper constructible surjective op into bun. Yeah, these are like, if I read this backwards, it looks like the inclusion of a dot into a circle with a dot. The point is I'm reading it backwards that way. And likewise here, the phenomenon like this locally is like, if I read it backwards, it's a proper constructible map this way that collapses something. There's 2 other classes of morphisms. There's refinements, not op. That sits inside of bun monomorphically. And then the final class is open embedding. Sits inside of bun monomorphically. These are 4 classes of morphisms. And it turns out these generate all of the morphisms. In fact, so I'll give these names. I'll call these ones closed. So morphisms in here coming from here are closed morphisms, just a name, because it corresponds to like the opposite of closed embeddings. This class, the remaining three, I'll call active. You might also read this as inert. And this is true if you know about those words. These we'll call open maps, because it's open embeddings and refinements, both of which are in particular homeomorphisms onto their image as just underlying spaces. And these creations, I mean, I'm not going to come back to this terminology so much, but I hope the terminology actually helps you think about this. Yes?
So to construct this infinity category bun, I can just pull back under bun to the simplex category, then verify the C conditions. And then all this is doing what we're doing is pulling it back.
Yeah, that's... yeah, no, that's a good question. So in other talks, I would just tell you bun as a simplicial space and not talk about all this background. For one, the background will be useful for later stuff. I think it's interesting on its own right and so forth. But to verify that bun satisfies the Siegel condition, makes use of, so originally trying to prove that bun was a Siegel space, just having it defined on simplices, was extremely hard. You want to use geometric arguments like you want like open subsets of simplices to be examples of simplices. Like just saying open subset of a topological simplex, that takes you outside of the combinatorial land. And really, I was taking open subsets because I wanted to be taking open covers, and you could replace that by a subdivision of simplices. And this is along the lines that Jacob Lurie's proof that the exit path category of the Rang space satisfies inner Horn filling. And it's just really hard to work with that. So it's possible, but I actually couldn't even find a proof using subdivisions and stuff. Like I wanted to choose vector fields to flow. Just all of the package the differential topology gives makes it useful to prove that bun satisfies the Siegel condition. So since you're already stepping outside of the land of combinatorial stuff to prove that bun was a Siegel space, then you might as well consider it in its natural home. I hope that addresses the question. Thanks. So fact. Oh, that's awesome. So you can always first do a closed map and then do an active map. For base finite sets, this is like inert active factorization, if you know that. And that proves very useful. Okay. So now, so this is the main example. Bun receives it captures everything I would personally want to for my agenda, I suppose. So to demonstrate that, let me modify bun, because it's a little bit too wild. It's comprised of all stratified spaces, and really I only care about stratified N manifolds, possibly with various kinds of structure on those N manifolds, maybe along the lines that Oscar talked about in his series, that kind of structure. And I also, I want that structure to interact with the stratification in a particular way. So bun is like, think of it as like unoriented manifolds. And I'm about to talk about structured manifolds, like oriented, framed, and stuff like that. So you can imagine a totally general account of what's meant by a tangential structure. But let me just say it for a Vera framing. So a framing of a smooth manifold is an isomorphism of its tangent bundle with a trivial bundle. So to say what a Vera framing is, I'll tell you what the tangent constructible bundle of a stratified space is, what the appropriate notion of the trivial constructible bundle is, and then a Vera framing is an equivalence between those two things. So I need to phrase tangential data. So doing this in a homotopy coherent fashion is awkward and redundant to do explicitly. So because once you know what it is for Euclidean spaces, it should tell you what it is for all stratified manifolds. So let's go over what the tangent bundle is for ordinary manifolds in a way that easily generalizes. Okay? So tangential data. So I'll spend a while on just the case of smooth manifolds. And this will look overly complicated, but remember, this is so that it easily generalizes. So, so for M, a smooth manifold, of course, we get its tangent bundle. And that's a locally trivial vector bundle, from which we get a sheaf by looking at sections. I'll call that theta sub m. I'll put an upper delta for, this is a discrete version of something I'm about to make continuous. So this is a sheaf. It sends open subsets U of a manifold to sections of Tm restricted to U over U. And that's some infinite dimensional vector space over the real numbers. So that's what we can do from our tangent bundle. We can look at this sheaf. So what I've described, this thing, theta for tangent, this is an element of sheaves valued in the category of vector spaces on the manifold. Okay, so that's how I want to think of the tangent bundle. It's a particular example of a vec-valued sheaf on the manifold. What? I'm about to remove that. So delta for discrete. So this vector bundle was locally trivial, and that's actually not being accounted for by this articulation. So how, what's the structure that tells me that this is locally trivial? Well, so here's one way of saying that. Let me modify the category of vector spaces from being an ordinary category to being an infinity category, a topological category, exactly so that its underlying groupoid is the disjoint unit of BGLN of R's, as topologically topological groups. So vect, notice the curly notation versus the straight notation, is the infinity category associated to, so I'll tell you what it is as a complete Siegel space. I'll continue the definition here. This complete Siegel space assigns to bracket P the collection of maps of vector bundles over delta P. So just, delta P is a regular topological space. So these are all vector bundles. And each of these maps is not any old map of vector bundles, but it's of constant rank. So as you move around by looking at fibers over this, the rank of these maps of vector spaces does not change. Constant. Yeah, it could be described that way, but yeah. So, oh, sorry, I feel your comment now. There, I mixed up a P and a bullet. So this is a bracket P goes to this simplicial set, or thanks, Hero. So let's see what the space of objects and space of morphisms are. So vect tilde, so the underlying groupoid of this infinity category, is identified with the disjoint union of BONs, orthogonal groups. And the morphisms between Ri and Rj can be described as follows. It's a disjoint union over dimensions less than each of them of O of I mod O of I minus D, O of J mod O of J minus D, crossed over O of D. It's like an amalgamation of Grassmanns, yeah? What? Oh no, so this, what's that? Yeah, there's a base. So I mean constant rank in the base. So if I look at a fiber over a point in here, I see a map of vector spaces, and I want that to be the rank of that to be independent of the point I chose to look at the fiber. So this is an adequate description of this infinity category, and here's why I consider it. Is because this being locally trivial, I can exploit as the fact that this, when I change vect to curly vect, is not just any old sheaf, it's locally constant. So first, Tm to m locally trivial means I can modify things and get now, so that delta is not there, this as a sheaf valued in curly vect of m, and as so, in fact, it's locally constant, LC. So that stands for locally constant. And what do I mean by locally constant sheaves valued in some infinity category? You might have a definition of that in mind, and that's probably a correct one. And here's one that you could take. So you could read this as a definition if you like. Really, it just means a functor from the underlying space of M, so here regarded as a groupoid. So just its underlying space into curly vect. So this constructible, or this the tangent bundle, gives me a functor from M, the underlying groupoid, into curly vect. That's just to say it's a local system of vector spaces. Would you mind wetting that? Thank you. What did you say?
Is curly vect finite dimensional vector spaces?
No, I didn't. It does no. Well, to say constant rank. So okay. I'll say yes, and that makes this definition important. Yeah. So I'll say yes, and what I mean by this is actually that. You could have said that something else and make that into a theorem or something. Yeah, that's right. Well, and locally constant rank. What did you say? Yeah. Oh, what? Yeah, definitely not. Yeah. But the stocks are finite dimensional, and that's what this sends a point to its stock. Yeah. So heuristically, and I'll give you a precise definition and this one is the one that I'll generalize. But I'll say now, how do you get this functor? One way of doing it is to choose a connection on your manifold. That gives you a functor from the path infinity category to vector spaces, to curly, to here. And that choice of connection is a contractible choice, the way things are set up. So that was no choice. Thanks. Thank you. So it produces for me a vector bundle over the 2 simplex. That's what a 2 morphism in curly vect is. That's what a composable pair is. So let me tell you how to describe theta m in there right now in a precise way. And the idea is that what theta m is the associated like parallel transport system to that vector bundle. But honestly, if you make me make that precise, I would just give you the definition I'm about to give you. So lemma / definition. So it's a definition, but for it to be a definition, you'll see. Oh, whoops. Second, so that was the first manipulation. The second is, so now, the fact that the tangent bundle of a smooth manifold is locally the same as a chart of that smooth manifold means I shouldn't have to tell you what this is for every manifold. I should just tell you what it is like as a sheaf on the site of all smooth manifolds, and then just say on Rn, it's Rn. So the trouble with doing that is that the tangent bundle is not a sheaf. on on the side of smooth manifolds. It just doesn't pull back. It's not even a presheaf, right? Given a smooth map, you can't pull it back one tangent bundle to the other. So how do you account for that? And there's some beautiful language for doing that I'll do right now. Some of you might be familiar with this. So so look at the category of smooth manifolds, and those smooth maps among them whose differential is of constant rank. Immersions and submersions are examples, so are subimmersions, and that's all of them. So that's what that is. It's an ordinary category, and there's a functor from its opposite to infinity categories that's given by sending a manifold to its category of locally constant vect-valued sheaves, by which I really just mean functors from its underlying space to vect. And I will denote this as, so again, like that. So given any functor from the opposite of something to infinity categories, there's a formal thing you can do, which is build a new thing over manifolds, so that an object over a manifold is the data of an element of the category it's assigned to. That's a Groton deconstruction, or the unstraightening construction. So there's an associated Cartesian fibration that I'll denote like this. This is a Cartesian fibration. If you don't know what that is, that might be a problem session type thing, or ask your neighbor. And this is, so I'm going to make a statement that I think motivates this way of thinking about a functor very well. Oh, yeah, sure. So here's a fact about this. About this functor, is that it sends open covers so open covering diagrams op to limit diagrams. This is not just any old functor to cat, but it's a sheaf valued in categories. So this sends open covers op go to limit diagrams. That's what this functor, it has that property. And that will be, that's useful, maybe more in the background. So lemma / definition is the tangent bundle of of all manifolds at once is the unique section with the following properties. Before I say what those properties are, I want to say what's advantageous about this point of view, and it's inside of, it's just there with the definition of infinity operands. If you've seen that, and it's a point that I think is underemphasized in infinity category stuff. So there's an equivalence between contravariant functors to cat and Cartesian fibrations over cat, where the morphisms of these preserve Cartesian morphisms. So why manipulate this data into this one? Well, this allows for the contemplation of, like, I'll say global sections of this sheaf that are only lax. They don't pull back strictly, just like the tangent bundle. The tangent bundle is a perfect example of something geometric. It's not like far away. The tangent bundle doesn't pull back, so we don't expect it to be a section of this functor. But we could expect it to be a section like this that's just not a Cartesian section. It doesn't send every morphism to a Cartesian morphism. So, but it does send some. So I'll record that here.
Is there a way to say in more down-to-earth terms what this next pulling back means?
That I don't mean, I just mean, this is what I mean.
Yeah, this is what it is, and there's no...
There's an intuition behind it, but that's what it is. Yeah. It's a section. And the fact that it doesn't send every morphism to a Cartesian morphism accounts for an intuition of laxness. So, so such that theta carries open embeddings. Those are examples of constant rank smooth maps to Cartesian morphisms. So note, it's not every morphism that goes to a Cartesian morphism, just open embeddings. So in other words, i.e., given an open embedding, I'll say u into m, call it f, an open embedding, then that determines a map of tangent bundles, and so therefore sections from sections on u to the pullback sheaf, so to sections over m. And you get this for every map, but what's special about open embeddings is that that map is an equivalence. That's the assertion that it sends something to Cartesian morphisms. And the second part, so I'm saying this is the unique thing satisfying some properties. That's the first property. Here's the second, is that on Euclidean spaces, it's standard. I'll just say is standard on Euclidean spaces. So in other words, so theta of Rn, that's supposed to be a functor from the underlying space of Rn, which is just it's contractible, it's a point, into vect, and just the map from point to vect that just plucks out Rn. So then I'll say the only point is 0 to Rn. So that's amazing. Once you specify what it is for Rn, that specifies it in general. That's the lemma aspect of this definition. And it's the unique thing satisfying that. That's the tangent bundle. That's the ordinary tangent bundle that you know, but phrased in a just terrible way maybe, or a very nice way. And this way is what accommodates the generalization to stratified spaces that I hope to explain before we're over.
Could it be non-standard for Rn, even though it does not independent to the vector bundle?
It could be. You'd have to make a choice of vector bundles that's, yeah, it doesn't have to be standard. That's a choice there.
What if we did something very naive, like take the calculus definition of tangent vector
Yeah.
as equivalence plus of paths?
Uh-huh.
So why not just do that, but do it for paths that are allowable, like only for exit paths?
So it can't be for, it's exactly the non-exiting paths. That's right. And I'll also say that it should be done like homotopy coherently. And I think there's an approach along those lines. But once you know it for Rn, that should determine it everywhere. And everything else you do from that is a little bit inefficient, maybe. It's good for understanding what it is, but for...
These are kind of,
Yeah,
Kind of question. Not transversal to the exit path.
that's right.
Is your constant rank is locally constant or really constant? Or it's not important?
Oh, well, because the simplex is connected or contractible, then that doesn't matter, unless I misunderstand your question.
Category man constant rank.
Oh, okay, what about that?
If you really mean constant or locally constant, if the manifold is not connected.
Oh, yeah, locally constant. Yeah. It's the Groton deconstruction applied to that functor. This might be a problem session thing. So there's a formal construction that does that for you in vast generality. Okay, so let me discuss the stratified case. Let me make a comment right now. So I got a number of kind of questions and comments after my talk yesterday that were of the form, like, why can't you just? And no, I encourage, like, those are good questions to ask. But my answer is usually the same, so I'll say it now. You could just, but there's a goal in sight, which is totally homotopy coherent invariance of manifolds. So once you start making any choices of points or explicit descriptions, you're making your life a little harder, because then you have to show that all those descriptions that you made respect automorphisms in a homotopy coherent way. And so it's convenient to be hands-off in this. And then come down with an example later on instead of carry the examples all the way. So so likewise, we have strat locally constant rank. So that's stratum-wise, locally constant rank. Op to infinity categories. So the reason I set things up like this is, again, so it generalizes. And this is given by setting a stratified space now to functors, not from the underlying space of X, but from the exit path category of X into vector spaces. And you could take this as a definition. CBL for constructible, just the definition, just words. So that's another functor. And just like right there, you can unstraighten this to get this Cartesian fibration. And just like before, and this functor here satisfies, it sends open covers op to limits, because exit sends open covers to colimits, as mentioned in pink. And this is something like, well, there's a lot that I could say about this formalism, but I hope this maybe looks like commutative algebras in an infinity operad. Lemma/definition. The tangent constructible bundle is the unique section. Theta, such that 1 is that, again, it's open embedding Cartesian. So it sends open embeddings to Cartesian morphisms. That's like saying whatever this thing is, it pulls back with respect to open embeddings. And the second is it sends blow-up squares to limits. To pullback diagrams. And that's the same as a relative pullback diagram because exit interacts as with push-out squares according to the pink. And then part 3 is, so this is just like saying it's appropriately local. And the last part says it's standard on Euclidean spaces. Well, Euclidean spaces with corners. Standard on Euclidean spaces with corners. So in other words, so theta of Ri cross with R greater than or equal to 0 to the j, that's a standard corner type or part of a face. This sends its exit path category, which is nothing other than the product of bracket 1 j times to vect by sending, I'll say A, which is a sequence of zeros and ones, to Ri cross Ra, where you interpret that as, you know, as and then it sends the post-set maps to the standard inclusions 0 into something else. I should say what some examples of this are, and then I'll stop. I'm not following.
So if you take something like delta 2 and you look at the corner around vertex 2, you can't give that a standard, rectilinear equivalence to Ri times R, greater than or equal to j.
I think maybe your comment is about how does this interact with automorphisms of the corners?
Right, but that corner, remember, not as something conical, but not something stratified, but according to your model from yesterday, some unstratified corner.
Let's talk about that later. So theta, so for this agrees with the usual notion for, so for smooth case, check. It's as usual. Let me just say what it is when you have a smooth manifold equipped with a properly embedded smooth submanifold, giving an example of a stratified space as mentioned before. So in this case, theta of this thing it assigns to each point x inside of W. That's some of the objects of the exit path category. The tangent space at x of W. It sends to points not in W the tangent space at that point of M which I could say m without w. And that's not quite all the data necessary. What about the link? So what about something in the unit normal bundle? And so to that, if I look at the link, it maps to w just by projecting, and it also maps into m without w by choosing with a choice of a normal bundle. And this is equipped with these maps, as just mentioned, into vect cross vect, given by, I'll just say, tangent bundle of w cross tangent bundle of m without w. And there's the arrows in vect. So what remains to specify to define a functor from exit is what this, so what is what that is. And I'll tell you, if I call this pi comma gamma, the two coordinates of that map, then this map is given as follows. So what needs to be specified is a map from the pullback pi upper star of the tangent bundle of w. So that's a fiber bundle on link to gamma upper star of the tangent bundle of m without w. That's what needs to be specified, is a map of vector bundles over the link. And what that is as follows. It's this threefold composite. Here's a zero section, the link into the link plus a trivial line. This map is the derivative of pi, but that goes the other way. So I'll just say the dual of that. Here I'm using that every vector space, so every object in curly vect is its own, or has a, so this is a contractible choice to make this map go the other way. It's tantamount to splitting a short exact sequences of vector bundles, which you can do upon the choice of connection, which is a contractible choice. So you make that choice to go this way. So this is why it's really hard to describe this in a concrete way and then try to hope that that will be ultimately functorial. And then this map is d gamma. And there you have the map that's required to specify that data. And this is how it goes in general. OK, sorry about going over time. Thanks for your attention.
We can still take a few questions.
Can you draw a picture of the last thing in a simple example?
Of this? A picture.
A toy example in which...
Yeah. I know how it feels when you see someone pick up chalk in this period. But so I'll try to not do that. So if you take W inside of M to just be R inside of R3 or something, so then you have a constructible vector bundle on R3 whose stock, whose fiber, at a point not on the line is the tangent space of R3, which is R3. And over on that special line, it's R. So now if you take a path that starts on that line and leaves it, what's the associated map of vector spaces? Well, in this very simple case, it's just the inclusion of R into R3 as the first coordinate. I don't know if that helps. And I said,
of which direction.
yeah, exactly. I guess, yeah, I had in mind it was the first coordinate, but yeah, that's right. And that's how it is locally.
I'm wondering, in your condition 2 on the lower board and 3 on the upper board, this being donut on our end, does this also mean for math between our end and this?
Yeah, exactly. So I just omitted that. So standard on Euclidean, it's not just object-wise, it's on the subcategory, the full subcategory of Euclideans. Does that answer the question? Yeah. Uh-huh.
Will we focus on pullbacks? Is there maybe somewhere like 6 factors and there could be a result in this framework?
So maybe we could have a conversation about that later. So that is part of the inspiration for Bun. It represents functors that are given as push-pull among stratified spaces that you don't expect on the level of sheaves because it's not a morphism of topoi.